How's everybody doing? How's cheer? We're doing the oral exams this week. We did probably the first 15 or so yesterday, and I think everything went well. The format worked well, the timing worked well, the technology has been working well so far. So yeah, if you're on that list for today, I'll talk to you guys soon. But for now, we're going to start the next unit, which is on alkanes, kind of, but it's going to be more about, we're going to look at molecular shapes in more detail than we have been. So it's important that your understanding of molecular shapes up to this point is good, meaning, you know, looking at a structure, identifying sp, sp2, sp3, identifying the shapes of those centers, whether they're tetrahedral, whether they're trigonal planar, or whether they're linear, bond angles, all that kind of stuff that we did way back in Unit 1 and a little bit in chapters since. It's going to become more important because what we're going to be doing is taking several of these centers and plugging them together to make larger molecules. And we're going to be looking at reactivity, and one thing that you're going to be learning about reactivity of organic molecules is that the shape is really important. You know, whether something reacts or doesn't react often will come down to the shape. And the other thing that matters in organic chemistry, maybe not in all pursuits, but is size. So size does matter in this course too, and we're going to be looking at that as well when we look a little bit more into alkanes. So alkanes, of course, are just hydrocarbons where all the atoms are carbon or hydrogen, and they're connected by only single bonds. If there's double bonds, they're alkenes. If there's triple bonds, they're alkynes. And this is just a map of Nova Scotia showing where a number of different energy sources are, but the one I wanted to point out here was natural gas, because natural gas is composed of alkanes. That's probably where we encounter alkanes most often, is in the form of, I guess we could say, fuels, you know, things like oil, gas, but, you know, and the things that are made from those, like lubricants as well. Plastics are generally made from oil. Many, many other things are made from alkanes as well. So they're the simplest organic compounds in terms of their structure because they have only single bonds. And generally speaking, alkanes have all carbons that are tetrahedral. They're all tetrahedral centers. And I have the three simplest ones right here: methane, ethane, and propane. You're probably used to or familiar with propane at least. Propane is, of course, what you burn in your barbecue. Methane is also called, it goes by a number of names, methane. Natural gas, sometimes it's called swamp gas. So methane, CH₄, and you can see their structures that you have right here with the boiling points on the slide as well. And one thing you'll notice about these three is that the boiling points are very low, you know, negative 160 degrees Celsius for methane. This suggests the intermolecular forces are very weak. Think of other small molecules like, I don't know, water. Water has a boiling point of 100, plus 100. So this is 260 degrees Celsius lower. So much, much weaker intermolecular forces. And that's because alkanes are nonpolar. They don't have anything going for them at all except for dispersion forces. Here's some exotic ones. So mostly alkanes have ane at the end of their name. And these are ones that chemists have, in most cases, synthesized, made from scratch, as opposed to found in nature. Lateраnes, though, are actually existing in the real world. There's been a lot of work. People spend, it's funny in chemistry sometimes, there are researchers who will spend a huge amount of effort to make something that's interesting or unusual, like what's on this slide, but maybe not necessarily have any sort of industrial significance or use or anything like that. Yeah, I'm just thinking of Woodward, Bob Woodward, not the guy who just wrote the book about Trump, but a guy who's now dead, who won a Nobel Prize in chemistry. He was the first person to make a complex natural product from scratch, to synthesize it. I think it was vitamin B12. And it took him 20 years and the work of over 200 PhD and postdoc students to make the molecule. And he made it in tiny yield. So like they couldn't make, using their methods, any significant amount of it to have any significant use. It'd be way easier to extract vitamin B12 from natural things. The significance of something like that, first of all, is that complex natural products are makeable, is the first one. Second, he developed a whole bunch of new chemistry trying to make it. You know, the reactions didn't exist to do all the steps that he needed, so he developed the chemistry to make new steps. In fact, 2 Nobel Prizes sprung out of that work. Very important still today. The last one here, you see Bastardane. He wasn't trying to make that molecule. He was trying to make a different one that had all 6 carbon rings. But you can see up at the top, that little ring there has 5 carbons. So he's trying to make it one bigger. Yeah?
So B12 exists that way, or like did he just make a synthetic version?
He made a synthetic version of it, yeah. Yeah. The structure was known. And of course, it's in plants or wherever you get vitamin B12 from. This one, this was not the one he was trying to make, but no matter what he tried, this was the only one that would be formed. So we called it Bastardane because it was like the unwanted child, I guess, which is not very kind, but anyway, that's what they went with. Alkanes are very important in biology as well. They're not just molecules that you dig up in oil and burn. We find them all the time in natural species. You see we have insects on the left. Alkanes are often used as pheromones in insects to attract a mate, for example, or warn predators or whatever else insects use pheromones for. You can tell I'm a chemist here and not a biologist, right? Apples as well. So this is an ant. And this is, apparently they have a little gland at the back where they release pheromones from. And I guess they have another one in their front, in their mouth, or in their head somewhere. But this is just a list of some of the most important alkanes that the ants produce as pheromones. And this comes from a very old paper, the Journal of Lipid Research from 1968. And you can see we have an alkane here, undecane, tridecane has 13 carbons. And then we have another one, pentadecane, has 15 carbons. And then we have a couple of these things. What's that? Or that? What functional group? Ketones. Good. Yeah. So ants make alkanes too. I guess if you had enough ants, you may be able to use them to produce gasoline. Big ant farm, then collect gas from them. I don't know how well that would work. This is another one. This is another paper from the Journal of the American Society of Horticultural Science. This is an older one too, published in 1998. Actually, I'm not going to say this is older. If it was published after I was born, then it's a new paper. If it's older than me, like the previous paper, then great. But you can see these are chemicals that are found in the wax of the apples. And you can see alkanes, depending on the apple, can be up to 40% of the wax that's on the outer coating of the apple. And what else do we see? Primary alcohols, secondary alcohols, aldehydes, ketones, these other common functional groups that we've been seeing kind of all along. Okay, structure of methane. I'm going to do this quick because we did this also in chapter 1, but I just want to hammer in the structure of an alkane carbon, of an sp3 carbon. So for something like methane, we know it's got bond angles of 109.5, ideal bond angles for something like methane. And the electron configuration, we know we take a 2s and a 2p, blend them together, we hybridize to make 4 times sp3. So this is what this looks like. These are the atomic orbitals on the left. They hybridize to make our 4 sp3, which gives rise to the shape, tetrahedral, everything 109.5. Doing this super quick because I know we've seen this already in chapter 1. Just a reminder, this is still important and always will be. Okay, so if you have a CH bond then in something like methane, it's an sp3 orbital on the carbon overlapping with the 1s orbital on the hydrogen. They overlap, you have a bond. Bonds tend to be strong with carbon. Carbon and other carbons, or carbon and hydrogen, or carbon and any row 2 element. Because they're similar in size, overlap is good. Carbon tends to form nice, strong bonds, which is important. That's, it's interesting to think that life, biology, pretty well everything is based on the chemistry of carbon. What is it about carbon that gives rise to its usefulness? Like, why didn't it pick silicon or some other element that's much more abundant on Earth? Silicon can make 4 bonds like carbon, but carbon makes stronger bonds. And so you want organic molecules to hang around for at least a little bit, and that's one of the benefits of carbon. Okay, isomers, we talked a little bit about in Unit 1. We're going to be getting into much more detail with isomers in this unit and in the next unit for sure. Constitutional isomers are the only kinds of isomers we've looked at so far. Constitutional isomers are ones where the order of connectivity is different between the different compounds, yet they still have the same molecular formula. So here we have an example of butane. Butane has 2 constitutional isomers. We have N-butane, where we take all 4 carbons and we connect them in a line. Fill all the octets by adding hydrogens, and you have N-butane. N stands for normal in this case. Or what you can do, instead of making 4 carbon chain, you can make a 3 carbon chain, 1, 2, 3, and then add a carbon off of the central carbon. So this is called isobutane. That's not an IUPAC name. It's not a systematic name. It's just what people often call it. These 2 compounds have different chemical properties and different physical properties, different boiling points, different strength of intermolecular forces, and so on, where N-butane has a higher boiling point. Okay. And we'll talk about why that is in just a minute. So if you have 5 carbons instead, then you can have an increasing number of isomers possible. You can have 5 in a row, like N-pentane, 4 in a row with what we call a branch, 1 methyl. So this would be kind of like 4 in a row with a branch. Or you could have 3 in a row with 2 branches. And again, these are isomers. They have the same molecular formula, different shapes, different connectivity, right? The atoms are sort of connected in fundamentally different ways. They have different boiling points. They would have different heats of combustion. They'd have different rates of reaction towards oxygen or whatever it is you're trying to measure. These are, for all intents and purposes, distinct molecules, distinct compounds, sort of unrelated to each other except that they have the same molecular formula. Okay. There's nothing special about isomers that makes them more likely to be reacting similarly. This is a table which shows the number of possible isomers for an alkane based on how many carbons there are in the chain. So we looked at C4H10, we said there was 2, right? We said there was this, and we said there was this. For pentane, you can see it on this slide, there's 3. For hexane, there's 5. And when you go down the list, you see it all of a sudden starts to explode. At 10, there's 75 different isomers. At 20 carbons, we have 366,000 different possible isomers. I should make that a question on a midterm. Draw all isomers of C20H42. One thing I've learned as a prof is don't give a question that is hell to mark. Because I've done that before. I give a question, like, this is a great question. And then I get the answers, and I'm like, how am I going to grade this thing? This is impossible. So yeah, I would never ask you for all, what number is that even? 62 trillion, if there's C40. C40, by the way, would be like, after about 40 to 50 carbons, it starts to become less of a liquid and more like a wax. So candle wax is probably some mixture of these things here, paraffin wax. So even when you have something like gasoline, And gasoline is a mix of a lot of different things, but there's a lot of octane in there. It's not just one molecule, like there's 18 different octane molecules. Gasoline would have C7, C8, C9, C10, all kind of mixed together in there, and hundreds of different possible isomers all kind of mixed together. So gasoline is sort of is a complex mixture of a lot of different things. Somebody online saying something. I hear some clicking. No, we're good. If you have anything, it's easier for me to see if you type in the chat. Okay, Alkane nomenclature. How many of you have done nomenclature of organic molecules like in high school? Roughly half. This is usually what I see. People, about half the time, people have done this. I'm going to spend no time in class doing Alkane nomenclature, but what I will do is put up like a video, kind of like the tutorial we had. There's tutorial PDFs already up on how to go through naming of these alkanes. This used to take up a lot of time. Like I could spend a week in class going through examples and naming these things, which often half the class or more have already seen or done. So I'm not going to do that. It will be important for you to be able to go through these steps though and name these alkanes for alkane chains as long as 10. So these are the names of what we call the base chains for alkane lengths up to 10 carbons. Methane, ethane, propane are the 1, 2, 3 carbons. Butane is 4. And then after that, it's easier because the names, the prefix is what's telling you the number. So pent means 5, hex means 6, hept means 7, oct means 8, non means 9, and dec means 10. Now, I'm going to share something with you that has bothered me for a long time. You don't notice we're in September, well, last month was September, right? What number does sept mean in September? What month is September?
9.
9. October, oct means 8. October is the 10th month. November, N-O-V, means 9. And November is the 11th month. December, D-E-C, means 10. And December is the 12th month. There, I got something to bother you guys for the rest of your lives too. Because they're not going to fix it, I guarantee you. Anyway, these are the numbers for the base chains. If it's a ring, we're going to be dealing with rings quite a bit in this course as well. It's the same names based on the number of carbons that are in the ring, except we put a cyclo in the front. So cyclo just means it's a ring, and so cyclobutane, a ring of 4 carbons. We'll be looking at these as well quite a bit. Okay, tutorial will go up on Acorn. I think it's actually already up on Acorn, and I'll add a video version of it as well. You can sit through if you don't like reading. And the idea is to go through, make sure you understand the rules. Typically, we, on a midterm, throw in a couple of questions on nomenclature, but we don't really focus on it too much. It's sort of one of those skills that I really hate teaching it because it's really boring. Students often love it though because it's a procedure, and if you remember the procedure, it works every single time, and you kind of just figure out the procedure and you can't be surprised, right? So that's the nice thing about these questions is, once you got it, you got it. To me though, Lewis structures are the same way. Lewis structures, there's a procedure, follow the procedure, it will always work. So, I don't know. Do you like drawing Lewis structures? Not people's favorite. All right. So it's important though that we do have these systematic ways of naming compounds because it used to be not the case. It used to be people in different regions would call things different names. Some of these names were very interesting and colorful. I sometimes come across in my own research old papers that name compounds things that are like arcane names, and it takes me some figuring out or some Googling at least to find out what they're talking about. Like for example, a few years ago, I was trying to repeat some procedure that was published in like 1905. And it was like, once you get your crystals, wash them with rectified spirit. I'm like, what the heck is rectified spirit? And then, you know, you Google it. I couldn't even find it. And eventually I talked to, it was an old professor that I knew. I was like, what's rectified spirit? He's like, that's another name for ethanol. And I was like, okay, great. But like, so that's the problem, not just within English-speaking countries, but different countries which speak different languages. If chemists are attempting to communicate with each other and we all have different names for things, it becomes very complicated, very difficult to communicate, and very difficult to share your ideas, right? Or share your results, share your what you've learned. So IUPAC has come in. IUPAC is the International Union of Pure and Applied Chemistry. Those of you who are on the Instagram for the course have noticed maybe there's a post yesterday talking about definition of an alcohol versus a phenol. That's IUPAC that makes these decisions, International Union of Pure and Applied Chemistry. So they have this booklet of rules. It's like 250 pages of rules on how to name compounds. We're going to do like the first 2 or 3 pages because no chemist needs to know all the rules. We have computer programs where those rules are programmed in, and you can draw a structure and it'll give you the correct IUPAC name for it. But for small molecules, it is important that you do know the rules because you'll encounter these names a lot, and ideally, they're familiar enough to you that if you hear the name, you can imagine the structure. I think about this sometimes too. I think about many disciplines that you might study kind of has like its own language. Oh, here's a question. Regarding yesterday's Instagram questions, would phenol still have the higher boiling point? I think phenol does have a higher boiling point, but it's not because of the OH. I think it's because it's flat. I might be wrong about that, though. I'd have to look that up, Lizzie. Yeah, I was talking about language, how every discipline kind of has its own, maybe not language, yes, language, but it could be written or spoken. And I think of like music, for example. If you're a musician, the language of music would be like sheet music, right? Where you write it out, there's notes and there's the staff. And if you're a musician, if you're a very accomplished musician, you could look at a piece of music and maybe, I've never gotten here, so I don't know if this is true, but maybe you could look at the notes as written and hear music in your head. I certainly know people who can look at music and just play it, sight read it, right? And to me, that's like a level of understanding where the language and the practice kind of merge together. For me, for example, I took French in school all the way going through, and when I learned French, you know, I never became fluent, but certain phrases I could sit down, I could translate the phrase into English and then understand it. And it was really slow. I couldn't speak conversationally. But I think chemistry is like that too, and the language of chemistry is structures and maybe to a certain extent names. And I can look at a structure and immediately get information from it, right? I can read it, I can zero in on the important parts, where for most of you, since you're new to organic chemistry, you're probably not there. But this is the goal, and this is why it's important to me as well, not just for you guys to know naming, but to be able to look at a structure and identify atoms and say sp, sp2, sp3, trigonal planar, tetrahedral, you know, and see those shapes. I don't know if that was a coherent point or if I wandered a lot there, but anyway. How about this compound? This compound has an IUPAC name. The IUPAC name for this one is 2R, 3R, 4S, 5S, 6R, 2, 2S, 3S, 4S, 5R, tetrahydro 3,4-dihydroxy 2,5-bis hydroxymethyl furan 2-il-oxy tetrahydro 6-hydroxymethyl 2H-pyran 3,4,5-triol. Simple molecule, right? This goes by a simpler name, which isn't popping up for me. Sucrose. So I'm not saying these systematic names that we're learning are the be-all and end-all. Often, for reasons that may be obvious from this slide, we don't always use the IUPAC names. It's important that they exist, and maybe the computer program can unambiguously create a structure from that name, but often we will be defaulting as well to common names, okay, for reasons of expediency. All right, where do we get alkanes? Mostly from oil deposits or underground gas deposits like shale gas or natural gas that you find underground. And this is a picture actually my wife took of, this is just outside Calgary, so just a little oil well there. So oil is a complex mixture of a whole bunch of different alkanes, and what they do is they go into a refinery. Anyone want to guess where the largest refinery in North America is? Not Alberta. No, not Nova Scotia, but you're getting closer. New Brunswick, yeah, St. John. Yeah. Oh, good job, Lily. Yeah. Apparently the single largest one, now there'd be a higher density probably of refineries in Texas, but they look like this, as you can see in the picture. And you see these really tall stacks, right? What this is a distillation column. And in lab, under normal circumstances, you would be doing distillations in the lab. And what happens basically is you have crude oil, as you see here, it's put through a furnace to heat it up, and then it's injected into this tall column. And what happens is the different boiling points determine how high up this column the different compounds can go. If it's a very light compound, you know, petroleum gas, if it has a boiling point of like 20 degrees Celsius, it can travel all the way up to the top and come out here. But if it has a boiling point, let's say of around 200, it'll condense into a liquid in this region here of the column. It will then run down and be collected out here, which will be kerosene. We have the 300-degree fraction is diesel. Industrial fuel oil, this is what people will often burn for heat. Things like furnace oil, or sometimes bunker C is another one. It's a really dirty version of this. Up here, gasoline. And gasoline is the most valuable fraction because everyone needs it for their cars. And there's other chemistry people will do and take the heavy ones and crack it. It's called cracking, hydrocarbon cracking. Not fracking, that's something different. Cracking breaks long chains into short chains. So you can convert things like fuel oil into gasoline. All this, by the way, is based on difference in boiling points. And boiling points are a function of the strength of intermolecular forces. And the only intermolecular forces available to alkanes is what? Dispersion, yeah, because they're not polar. Okay. So what governs the strength of the dispersion forces? Generally speaking, we would say that dispersion forces get stronger as you add in more electrons because they're temporary dipoles set up by causing electrons to shift temporarily. So it follows then, I guess, if you have more electrons, you're going to have more dispersion. Yes? We're going to get to that in just a minute. And the answer is no. Isomers will have different ones. So generally speaking, if you add more carbons, the boiling point goes up. Right? So here's an example. We have heptane, octane, nonane. These are just straight chain carbons, so basically very similar in shape. And you see the boiling point goes up here by what, plus 27? Goes up here by plus 25. So adding a carbon makes the boiling point go up, partly because you're adding a bunch of more electrons, right? You're making it heavier. So maybe that's another way to think about these. As molecular weight increases, dispersion increases as well. And dispersion forces can get very strong if you have big molecules, like waxes. Very long chains of 30, 40, 50 carbons. They have a high enough boiling point that or high enough intermolecular force strength that they solidify, they turn into solids. And you can have hydrocarbon chains that are like hundreds of thousands of carbons long. And this is plastic. This is polyethylene. Polyethylene plastic would just be an alkane with super, super long chains. And polyethylene is a hard plastic as well. All right, so that's the first one. Increase the number of carbons, increase the boiling point. This is a plot showing the boiling point, the purple line here, or the pink line, top one, versus the length of the carbon chain. These would be for a straight linear chain, and it's pretty regular. Melting point as well goes up, but melting point you see is a little more jagged, and that's because there's more factors that go into melting points. Shapes matter because how well they pack into a crystal solid affects the melting points, which we don't really want to discuss too much here, except to talk about the strength of intermolecular forces. Now, to answer your question about what happens if you have isomers. Well, here's an example. These are the three isomers of pentane. We have N-pentane, 36 degrees, isopentane, 28, neopentane, 10. So these are all isomers, obviously with different intermolecular forces because they have different boiling points. So another factor which is important for determining the boiling point of an alkane is the surface area. And I want you to think for a second about boiling a pot of spaghetti. Okay, and you have these long strands of spaghetti and you put them in, you boil them, they absorb the water, and you pour them into a colander and you drain the water out, and you have this sort of mass of cooked spaghetti sitting there. Did you ever do that and then, I don't know, get a phone call or get distracted and come back and like 10 minutes later, it's like one big, ball of, and you can't separate them, they're all stuck to each other. Now imagine doing the exact same thing, except instead of using spaghetti, you're going to use penne. Right? You know what penne is, right? Yeah, penne is like they're like tubes, they kind of look like, but they're like shorter and they're fatter, and the same thing will happen. They'll stick together, but it'll be much easier to break them apart, right? Is there a kind of pasta with spheres? Probably, is there? Gnocchi, kind of. Gnocchi's kind of got other stuff in it, potato and... But anyway, my point is, things that are long and stringy have a lot of surface area. They will stick very well to other spaghetti strands, and you get this sort of big jumble of them, which is extremely difficult to separate them apart. However, if they're sort of compact and kind of ball-shaped or close to being ball-shaped, more approximately ball-shaped, they'll have less surface area for their weight or for their size, and won't interact as strongly with their neighbors, and therefore are easier to separate. So the molecules are the same way. If you think of something like N-pentane, this is like our spaghetti. This is long and thin. Maybe it's not super long, but you get the idea. It's long and thin. It has a lot of surface area, and it can get up against other molecules that are the same, and there's relatively strong dispersion forces with this shape. For something like neopentane, it's kind of ball-shaped, right? Like this one's more, I don't know, we'll call it hot dog-shaped. Hot dog-shaped and meatball-shaped. Sorry if you're vegetarian. So something like neopentane has relatively low surface area. It doesn't stick as well to its neighbors just because it doesn't have as much surface area. And so its boiling point is going to be much lower than something that's long and thin. So that's basically it. For isomers, the surface area is what, because they have the same number of carbons and hydrogens, surface area is what will distinguish which one's stronger. Another one, we're going to talk about cyclic alkanes or cycloalkanes. A cycloalkane will always have a higher boiling point than the same linear carbon chain with the same number of carbons. So you see octane is 125, cycloalkane is 151. I find it hard to explain why this is the case in my own mind. Apparently this like disc shape though, to me, obviously it looks more ball shaped, but however it is, these can interact more strongly with each other than the straight linear chains can. Maybe it's because the linear chains can kind of ball up as well. They're not always long, and maybe some of them get compact, where this is always sort of, it's like a plate, right? In fact, actually, we're going to look more in detail at what the shapes of these things are. But if they're flatter, they're easier to stack, they can interact more, and surface area, whatever it is, they have higher boiling points. We know this for sure.
But doesn't cyclooctane occupy less surface area than the linear one?
Yeah, so the question that just came out was, does cycloalkane have less surface area than the linear one? I'm not sure. It might be that if this one balls up, like maybe if it's like, because all rotate, right? It's not just a bunch of straight things in solution. Sometimes they can ball up. Maybe on average, this one is higher. That's my best guess. It's funny, this is kind of a small minor point. Alkanes versus cycloalkanes in terms of their boiling points. Most books don't even bother treating it, but I like to give you guys that just. Stability. Now, stability is another question altogether. Stability has to do, well, stability of alkanes has been a very important topic of research. People were very interested in which ones are more stable and less stable, because things that are very stable, when you burn them, don't give off as much energy as something that's unstable. And the main reason people have been interested in alkanes for years is because we can burn them and get energy out of them, right? We use them in power plants, we use them in cars, we use them heat your home or whatever. So almost every alkane that's accessible has been measured in terms of the amount of heat you get when you burn it. And that's also called the enthalpy of combustion or heat of combustion. You may remember learning about this in first year chem. This is just like an Arrhenius plot showing if you have an alkane like this one, which is octane, and you burn it, there's an activation energy, EA, and it gives you 8 CO2 and 9 water. The difference between your initial energy, which is this, and your final energy here, is your delta H, and sometimes we often call it delta H of combustion, because this is a combustion reaction. We're burning it and we get off. So if you were to look at a bunch of isomers of this compound, of octane, what you would see is that different isomers will give off different amounts of energy. And one thing is we can use the amounts of energy they give off to compare what their starting stabilities were. So first of all, if we take heptane, octane, nonane, and you burn them in a, what's the piece of equipment you burn things in to measure delta H's? Calorimeter, great. So we did that in first year. We did the bomb calorimeter and a coffee cup calorimeter. These will go in a bomb calorimeter. And I don't know, people have bought bomb calorimeters and measured every alkane they get their hands on. And so we know very well for heptane, delta H of combustion is this number, and for octane and then nonane and so on. Is this surprising to anybody? You add more carbons, you get more heat out of it. Probably not super surprising, right? You get more heat out of a long piece of wood than a short piece of wood if you throw it in a fire. Yeah, okay, that makes sense, right? In fact, if you look, the jump turns out to be identical going from 7 to 8 as it is from 8 to 9. So that's one thing that should be unsurprising to you. Increase the number of carbons in the chain will give off more energy. That's because it's consuming more oxygen, generating more CO2, and generating more water. No surprise there. But if we look at alkanes that are isomers of each other, these are all C8H, what would that be, 18? These we can directly compare because they all give the same products. All of these, when you burn them, give the same number of carbon dioxides, the same number of waters, and consume the same number of oxygen atoms. So they all kind of end up in the same place, which you can see at the bottom here. So if you measure their heats of combustions, which are all these values here, 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 you can figure out what their starting positions must have been relative to each other. And their starting position is their stability. The lower down it is, the more stable they are. The higher up it is, the less stable they are. So a common way of trying to understand the relative stability of molecules, one way to do this is to burn them all, see what products you get, measure heats of combustion, and use those to compare for starting energies. This is actually how they measure heats of formation for most compounds, is they do some calculations based on heats of combustion. Because heats of combustion are easy to measure, you just need a calorimeter. There goes the end of my, okay, I'm good. So what are these numbers? They're similar. The linear one, octane, is negative 5471 kilojoules per mole. If you have 7 and a branch, it's a little bit lower. The heat of combustion is a bit lower, which means the branch one is slightly more stable, 5 kilojoules per mole more stable. If you make it more branched, right, this one has 6 carbons and 2 side chains. It's 8 more stable again. And this is like the most ball-shaped you can make this octane. This is like a 4-carbon chain, 1, 2, 3, 4, with 4 branches, 1, 2, 3, 4. This is the most branched, most highly branched version you can get, and it is more stable again by another 6 kilojoules per mole versus the previous one. So this is an experimental observation. The more branched an alkane chain is, the more stable it is. The lower its heat of combustion. Yeah. Why, you might ask? And actually, this is a really, really complicated question. And there's not an easy solution for it. Actually, it's not even well agreed upon why this is the actual case. I've seen lots of papers on this. There's a phenomenon called proto-branching that some people believe is not real. There's a lot of computational work being done. So at this point, all I want to say is people are trying to figure out exactly why this is the case. There isn't wide agreement, but at the moment, you can rest well knowing that it's an experimental fact that branched chains are more stable than unbranched chains. So if you could buy a kilogram of one of these to burn in your furnace to heat your home, which would be the best one to buy? This one. The one with the highest heat of combustion, the one that's the least stable. You want to get the most energy you can out of it. And this is an important consideration. There's lots of fuels where, you know, how much energy you get out per mass really matters, especially if you're into like racing. You want high energy fuels, or also like if you're flying a rocket up to space, you want to get a lot of energy out of a small amount of fuel. Now, rocket fuel doesn't use alkanes, but certainly vehicles do. Planes, for example. If you're flying a plane, you want to get a lot of energy for the mass of fuel that you have. You don't want a fuel that doesn't give you a lot of energy. So airplane fuel will be a higher grade. For your car, it's less important, although still, I guess, you don't want to be dragging around fuel. Like you wouldn't want wood. Fill the back of the car with wood and keep throwing logs in, but actually that might be kind of cool. Someone should invent a car like that. It'd be like a steam engine, you know, like the old trains where they'd shovel coal in as they kept going. Same kind of idea. Oxidation and reduction, very important in organic chemistry, particularly in organic 2. We do a little bit of oxidation and reduction in organic. In first year, you did redox, you do balancing redox equations, and you do a whole unit on electrochemistry. In organic chemistry, it's a bit different. We don't really assign, I mean, you can assign oxidation numbers the same way, but we generally don't. Typically, what we do instead to talk about oxidation of carbon, at least, is count the number of bonds from oxygen to carbon and hydrogen to carbon. So we think of oxidizing a carbon as increasing the number of bonds to oxygen or decreasing the number of bonds to hydrogen. So methane, we would say, is completely reduced. It has the maximum number of bonds to hydrogen and the minimum number of bonds to oxygen. So we would be oxidizing it by adding one bond to oxygen to make methanol, oxidizing it again to make two bonds to oxygen, a double bond here, to make formaldehyde, oxidizing it again to add a third bond to oxygen, and the most oxidized you can get carbon is CO2. So CO2 and methane are sort of opposite ends of the oxidation spectrum. Another way, if you look at this, each carbon in ethane here has 3 bonds to hydrogen. If you remove H2 and make a double bond, each carbon only has 2 bonds to hydrogen, or in this case, 1 bond to hydrogen. And so going up this way is also considered oxidation. So either removing hydrogens or adding bonds to oxygen. Yeah, so you know when wine goes bad? You know Louis Pasteur and his whole story about he was hired to figure out why wine was going off somewhere. It's because wine has ethanol in it. What happens under certain biological conditions is it can get oxidized to acetic acid. And actually, if you buy a bottle of wine and drink half and leave it on the counter for like a week, it'll start to do the same thing, and you can taste sour, right? It tastes vinegary. And in fact, that's how they make vinegar, or they historically used to make vinegar, is letting wine. That's why there's like white vinegar and red vinegar, because there's red wine and white wine and so on. But yeah, that's an increase in the oxidation state of the carbon. So I wanted to get that down before we go. Okay, so what we're going to be doing for the next chunk of this unit is great detail seeking to understand more fully the shape of alkanes. We know alkane carbons are tetrahedral. We know the bond angles are 109.5. We know they're all sp3. But that doesn't quite cover it. That covers each carbon center, but it doesn't cover the molecule as a whole, because we have this bond in the middle, the CC bond, that can freely rotate. Okay, generally single bonds can rotate very easily. So we kind of have those two carbons independently spinning of each other. And that can lead to a lot of different possible orientations, even just for 2 carbons. You can imagine a long chain with 8 carbons. If all those single bonds are spinning, it's a very floppy molecule. Go back to our piece of spaghetti, right? There's lots of different orientations of that spaghetti. You can twist it up in a lot of different ways. Okay. This is also the part of the course where people start regretting not getting a molecular modeling kit. And what we're going to be relying on, if you don't have a molecular modeling kit, is your spatial awareness, your sense of your ability to manipulate 3-dimensional space. Some people are just innately really good at this. And some people are really innately terrible at this. Just like some people have a really good sense of direction, some people don't. This can be learned to a certain extent. I think my ability to do 3D manipulations like that in my brain are pretty good, because I got through my degree without ever using a modeling kit. You may never need one either. Some people have a lot of difficulty, I've seen, visualizing what we're talking about until they get the kit, and then it all snaps into place for them. So depending on how you feel for the next couple of classes, you may consider trying to find one. But yeah, we're going to be thinking about these. Actually, last night I don't know how I even came across this. You know how sometimes you're online and you see sort of just random sites, and this was a test to test your 3D spatial awareness, your ability to manipulate objects in 3 dimensions. And it would have like a cube with like 6 different things, something different pattern on each side, and then they would lay it out flat, like unfold it and put it down flat, and you had to say which flattened out one matched the cube. So you'd have to fold it up in your head and then see what it would look like. These are the sorts of things, if you're good at that kind of thing in your head, this stuff will be a lot easier. I should send that test around, just you can see where you're at. Yeah, it's like those IQ tests. Did you still do those in school? We used to do them like every 3 years. We called them IQ tests. They were called like standardized, I don't know, provincial tests. And they weren't worth anything. They were just sort of like testing to see what you understood about math or whatever. We thought they were IQ tests. I don't know that ever a decision was made about my life based on the results of those tests, but yeah, I remember doing that a lot. You'd have like a little object you'd have to unfold, or it'd be like a piece of paper and you have to fold the paper and make a line, then unfold it. What would it look like? What would the line look like when you unfolded it? None of this is familiar to you guys. Those were good times. Michaela says IQ tests at restaurants. What are those? Ah, yeah, cool. Well, it's 9:23. I don't want to go anymore. We're done. I have office hours again today, starting at 9:30. I think 9:30 to 10. So if you are looking for me, I'll be online at that point. And I'll see a lot of you today for the quiz. If you have not signed up for a slot yet, which I think there's one person, maybe, please do sign up for one. There's lots of slots today and tomorrow still left. All right, thanks everybody. See you guys.